So understanding how an NMR works and how signals appear is a little bit tricky. And so lucky for you guys, more important than knowing how everything works is to understand how to read an NMR spectrum. Okay, so I'm going to leave everything a little bit gray and just tell you an idea of how NMR works, and let's read how to do it. So NMR uses nuclei that have certain spins. Okay, so you know how electrons have plus half and a minus half a spin. Certain nuclei also have spins. Okay, and two of the nuclei that we use often is hydrogen and carbon. Carbon is an isotope of regular carbon. And so what happens in NMR is these nuclei are subject to radio frequency. And so when it's being put into this field, the nuclei will either align parallel or anti-parallel to the field. And then that pulse is taken away and it will come back to its original form. Alright, so it will either anti or parallel, and then when you take it out, it will come back to its own self. And when it's doing that, it's going to give off some energy, and the NMR just captures that and sends the whole signal. And so what happens is, usually when you're doing NMR, you're going to dissolve your compound in CDCl3. And so CDCl3 is the deuterated version of chloroform, CHCl3. So why do you think you replace the H? So you know that hydrogens have a spin on their nuclei. Okay? So we do not want a spin in our solvent, because if we did, you would have a huge solvent peak, because obviously you have a lot more solvent than your compound, and your compound will come in here and you can't make anything from that. Right? So what NMR solvents do is they leave 10% of your compound with H's, so it'll be a relatively short peak. And we want this so we know exactly where our solvent is coming in on our scale, so we can just identify the rest of the pieces.
You said hydrogen has a spring, or what did you say? Spin?
Yeah,
okay.
So it doesn't show up in your animal. Okay, so you have to be really comfortable identifying the types of hydrogen to do NMR. And the types of hydrogen are identified by the types of things that the carbon that it's attached to is bonded to. So we'll get more practice with that. And so one thing you have to remember is equivalent hydrogens, if they're in the same types of environments, you only see one peak. They all come in around the same peak area, okay, regardless of how many they are. And if they have non-equivalent, then they'll come in at different peaks, and there's something else that will happen. Okay, so for this example here, actually I want a volunteer to come up and draw this. That long, I'll just copy it off the whiteboard. I can't anything together. Alright, just copy it. Just copy it. Okay. Alright. Copy, right? Okay. Not there. Not this. The compound. Oh, okay. So first of all, how many different hydrogens are there in this compound? Not different, just how many hydrogens?
9, 10,
12, okay? And so they labeled one of them as just A and B, right? So obviously, some of those are all the same, and the other one is all the same, okay? So from here, what you have to look at is, so identify the hydrogen and see what this carbon is attached to. Okay? This is only attached to oxygen, it has no other hydrogen, so this would obviously be on its own. And all three of them come in at the same time. Okay? This one is attached, so this CH3 group, this CH3 group, this CH3 group, it's all attached to the same carbon. Right? You'll have a bigger peak, yes. And we'll worry about that later. But first, right now, you just have to be comfortable taking out hydrogens and seeing if they're equivalent. Okay?
So that will have the
Because
same
they're all
signal?
attached to the same carbon.
The same signal?
You have the same signal, and they're also equivalent. Okay? So these type of hydrogens are non-equivalent with these hydrogens. But these hydrogens are equivalent with these. Okay? So even though you have 12 hydrogens in that molecule, you'll only see two peaks because there's only two types of hydrogens. Okay, so in your NMR, you have x-axis, which is labeled as chemical shift, and that's the value where it comes in. And you have 0 on the right side and higher numbers on the left. And they usually go up to 6. Sorry. Okay, so in our chloroform, which is our solvent for NMR, we usually add TMS, and it's just a standard that we add that comes in at 0, so you know that your spectra is calibrated. So where the peak comes in depends on the types of things that are around it. Okay, so if you have electronegative or electron withdrawing groups, the chemical shift will be higher. And if it's higher, the term used is downfield. So down is pushing it to higher values, upfield is pushing it to lower. Okay, so electron withdrawing groups, give me examples of that. Rebecca?
She say downhill.
So give me examples of electron withdrawing groups. Electron withdrawing groups. Give me examples of that. Someone help her out? You know this. I know you know this. Sorry?
Electron.
Are taking electrons away. Something like electronegative.
Electronegative, high electronegativity, like fluorine, OH.
All halogens. You have OH groups, things like that.
Will that
Have
include?
an OH group attached to a carbon that's also attached to a hydrogen that will push that hydrogen shift down because you have an oxygen attached.
Does that also include the ones on at the bottom of the column, the bigger ones?
Yep.
Okay.
And so, give me examples of electron donating groups.
Cations, sodium,
Not
metals.
Not metals. So CH3 groups are known to be electron donating. Okay, so anything CH3 will come in around 1.
Anything with a hydrogen on it. Okay.
So, looking at our example here, which one will come in? Which one's upfield or which one's downfield? It's already labeled for you, but A will be downfield. Why? So, rule of thumb, look at the carbon that the hydrogens are attached to. What is that carbon attached to? Okay? This carbon is directly attached to an oxygen, and oxygen is electronegative. Therefore, it's going to make these hydrogens shift down. Okay? This carbon, so first you look at the hydrogens and look at the carbon that it's attached to. And it's also attached to another carbon, and this carbon is attached to oxygen. So it's quite far away from that electronegative group. So this one will be upfield. So you know how to identify how many peaks will show up. You know where the peaks will come in based on things. But you will also have to know, obviously these will have an effect on each other, okay? And so we'll get into that. Actually, before that, we're going to do some examples. Answers are already up here, but I would like someone to explain things from them, okay? So, Tamara, for A, how many different types of hydrogens are there?
4.
Right.
Huh? How many different hydrogens?
Types.
Oh, types. Oh, 2.
2. And
I'm sorry.
so we have A and B, they were already labeled for that. Which one would be upfield and which one would be downfield?
A would be downhill and B